Scientific method. To explain a phenomena, the four steps involved in a scientific method are: number 1, systematic observations of a phenomena; number 2, formulation of a hypothesis to explain the observation; number 3, comparison of the findings of the formulated theory with actual observations; number 4, modification of the theory if necessary. Measurements and observation are the first and most crucial steps in the scientific explanation of a natural phenomena. There are two kinds of observations: subjective and objective. The objective observation is the same for all people. However, the subjective perception differs from person to person, observers. Only objective observations are relevant to physics. The next step is the formulation of a theory or hypothesis based on a set of laws to account for the findings. The definition of a successful theory is one that can both anticipate and explain all current observations. A theory needs to be updated if a new observation or measurement cannot be explained by it. A new theory based on new premises must be produced if the modified theory is unable to account for the new measurements or observations of the phenomenon. Such occurrences are common in the history of the development of science. Number 1. At first, it was believed that the earth was flat. The world cannot be flat, according to observations of distant ships on the water. As a result, the notion that the earth is flat was rejected and its spherical shape was assumed. The earth cannot be spherical, according to observations on the acceleration caused by gravity. The earth was then thought to have an oblate spheroidal form, like an orange. The exact shape of the world has now been captured on camera by Earth satellites. These images support the idea that the earth has an oblate spheroidal form. Number 2. One more significant illustration can be drawn from the properties of light. To explain the facts of shadow generation, Newton postulated that light has a corpuscular particle character. This hypothesis states that light is made of corpuscles or particles. This theory was unable to account for the phenomenon known as diffraction, which is the observable bending of light from the corners of minuscule obstructions. A theory was put to explain how light behaves like a diffraction wave. However, neither of these hypotheses was able to account for the observed photoelectric effect. Essentially, new notions were suggested in a novel theory to explain the photoelectric effect. The quantum theory of light was given to this new theory. There are other examples like these that unmistakably show how the development of conceptions and experimental findings are intimately tied to the advancement of physics.